In this video, we're going to go over an example that involves analyzing a refrigeration cycle. And so, in this problem, what we're dealing with is a refrigerator that's at 5 degrees Celsius, and the surroundings outside the refrigerator are 20 degrees Celsius. And essentially what goes on in this refrigerator is that heat transfer from the contents inside the refrigerator are going to transfer heat at a rate of 100 kilojoules per minute into the refrigerant that's cycling through the refrigerator. All right? And so this refrigeration process, we're looking at it when it operates at steady state. And once again, it's going to remove 100 kilojoules per minute of heat from the contents inside, allowing the contents inside the refrigerator to stay at 5 degrees Celsius. All right? And so the refrigerant that's actually cycling through the refrigerator is Freon 22, and its thermodynamic properties are depicted here on this refrigeration properties plot, and we'll look at it more in depth later on. Okay? All right, and so for the refrigerant that's cycling through the refrigerator, the material that's leaving the evaporator or the boiler is going to be at 0 degrees Celsius, and it's a saturated vapor. And the material that's going to be leaving the condenser of the refrigerator is going to be a saturated liquid at 25 degrees Celsius. All right, and so the compressor in the refrigeration cycle is going to operate at 75%. And so what we want to figure out in this problem is the required flow rate needed in order for the process to once again remove 100 kilojoules per minute of heat from inside the refrigerator. And we also want to figure out the rate at which the compressor requires work, or essentially the power needed for the compressor to operate. Okay? All right, and so with these pieces of information, what I want you to do here is I want you to pause the video and I want you to sketch out the refrigeration cycle that is occurring here. So with this information in the problem statement, we could sketch out a refrigeration cycle that looks like this. And so once again in the refrigeration cycle, it's actually somewhat similar to the Rankine cycle. And so we're going to have 4 different steps going on in 4 different streams. And so here in stream 1, it's going to enter in an evaporator or boiler that's going to turn it from a liquid into some sort of vapor. And in our case, we're going to be dealing with a saturated vapor at 0 degrees Celsius. This saturated vapor is then put into a compressor that is going to increase the pressure of the fluid. And we're told, that there's some sort of work rate going into the refrigerant, and that the compressor operates at an efficiency of 75%. This refrigerant comes out of the compressor at some temperature, pressure, and also some unknown mass flow rate. And then, once it's in stream 3, once it's at this elevated pressure, it's then going to go into a condenser where heat is going to be removed from the refrigerant, and that heat's going to go into the surroundings, which are 20 degrees Celsius. So it's going to go into this condenser, it's going to have heat removed, and then it's going to come out as a saturated liquid at 25 degrees Celsius, which is what the problem statement tells us. And we also don't know the pressure here or the mass flow rate. Then, after it comes out of the condenser, it goes through a throttle valve where the pressure is decreased, and it ends up back in state 1. And once again, in this evaporator, it's going to receive 100 kilojoules per minute of heat that comes from the contents inside the refrigerator. Okay? All right. And so that's the sketch of the refrigeration cycle. But before we go on through our analysis, we're going to want to make some assumptions. Okay? And so in this refrigeration cycle, just like in the Rankine cycle, what we're going to do is we're going to treat each of these different unit operations as a sort of open system. And each of these open systems are going to be operating at steady state. We're not going to change or care about changes in kinetic or potential energy. And then as far as the assumptions for each of the individual unit operations, for the compressor and the throttle, they're going to be adiabatic. So we're not going to worry about any sort of heat coming out of or into this throttle valve or the compressor. For the evaporator and the condenser, or otherwise, this evaporator is otherwise known as the boiler, they're going to be isobaric. So there's not going to be any sort of pressure changes there. And also in the evaporator and condenser, there's not any moving parts we need to worry about. So we're going to say the shaft work at those places is equal to 0. For our compressor, it's not operating optimally. In fact, we're told the efficiency, which is going to be 75%. And then once again, any thermodynamic properties we need for our refrigerant, we're going to get those from the thermodynamic properties chart in the problem statement. Okay? Before we get there, we're going to first derive some things in the problem. And before we start our material balances, once again, in this problem, we're going to be dealing with quite a bit of information. And so before we start dealing with all this information, what we want to do is actually kind of set up a table that will allow us to organize all of this information. And so once again, I recommend setting up two different types of table. The first table is going to list all of your different streams. And for each of these different streams, you want to have a row or a column dedicated to each type of different thermodynamic property. In the second table, we're going to list the different unit operations of the different steps the streams go through. And at each of these unit operations, you want to list, the change in the specific enthalpy, the shaft work, and then the heat that either goes into or leaves the system. Okay, and we know, that leaves the system. Okay, and here you'll notice that the way I'm writing the work and the heat here, it's going to be divided by the mass flow rate. Okay, all right. So keep that in mind for later on. Okay, in any case, now that we've kind of set up our tables, we could start to approach this problem. Okay, and in this problem, we seem to know the most information about the compressor because we know the properties of the stream going into it, and we know its efficiency. So I'm going to recommend that we start there in this problem. So we're going to start by doing an analysis on the compressor. Okay? All right, and so once again in this problem, we're told that the compressor is not reversible, or it's not perfectly reversible, but rather it has an efficiency of 75%. Okay? But in order to approach these sort of problems where we're dealing with a inefficient compressor or an inefficient turbine, the approach we want to take is to actually first solve the case, or solve for all the thermodynamic properties for the case where the compressor is reversible, and then use the efficiency to calculate what the thermodynamic properties are for the irreversible case. Okay, so let's solve thermoparameters for reversible compressor and then after we do that, we're going to solve for the irreversible case. It may not make sense now, but as we go through this analysis, it should become more clear what we're doing. Okay? Alright, so what we're going to do is we're first just going to solve for the case where we're dealing with a reversible compressor, i.e. the efficiency is, or the reversible compressor means that the entropy generated is going to be 0. Okay? So let's go through this sort of analysis. So we're going to go through our different balances. So we'll start with our material balance, dealing with a steady state system with no reaction. So input's equal to output. So our input to the compressor, we go here, is stream 2, and our output is stream 3. Therefore, M2 is equal to M3, which we'll just call M dot. Okay. All right, but we don't know M2 or M3, so we can't really figure out what M dot is right now. That's something we want to solve for eventually. So that's the material balance. We'll now move on to the energy balance. So we're dealing with an open system. So WC is going to be for compressor. And then we have the enthalpies of stuff going in. And the enthalpies of stuff going out. We're operating at steady state, so the whole left-hand side is 0. And the compressor is adiabatic, so we don't need to worry about that. Okay? And so here, remember, right now we're trying to solve for the reversible case. Or actually, to explain this better. So what we're left with right now is the compressor work, and remember these mass flow rates are equal. The compressor work is going to be equal to m dot of H3 minus H2. Okay? And so if we want to solve for the work of the compressor, what we need are the enthalpies of stream 2 and stream 3. For stream 2, we're told both the temperature of it and the fact that it's a saturated vapor. Okay? And so we have two pieces of thermodynamic information. And so just like the steam tables, in these sort of thermodynamic plots for refrigerants, if you have two pieces of information, you'll be able to find any other piece of information. Okay? So H2 in a bit, I'll go through how you would find the properties for that. But for H3, we actually don't know anything about it at the moment. Okay? And so, like I said, when we're approaching this problem, we're going to want to solve for the reversible case first. Right? So the H3 we're going to calculate initially, it's going to be the enthalpy 3 for the reversible case. All right? So I'll write it there for now. But in any case, we don't know enough information to solve for H3 rev. So we'll come back and solve for it later. So that's everything we could do with the energy balance for now. So our next step is to solve or go through the entropy balance. Okay? So our entropy of stuff coming in minus the entropy of stuff going out. We have our heat term and our entropy generated term. Okay? Once again, steady state, adiabatic. And then we're solving for the reversible problem first. So this S gen is going to be 0. We also know that these are the same. And because on the left-hand side we have 0 here, we could actually just cancel out the m. And what we're left with from the entropy balance is that the entropy going in is going to be equal to the entropy going out. Okay? So this is a relationship we've seen before for adiabatic systems that are reversible. But what's really interesting here, and so once again, right now we're solving the reversible scenario. What's really interesting here is we know all the properties of stream 2, enough to allow us to find the entropy. But now, since from the entropy balance, finding the entropy for stream 2 will now allow us to find the entropy for stream 3. Okay? And so that, and then somehow getting another piece of thermodynamic information, will allow us to look up any other properties for stream 3 as well.